Hello. All right, let's finish up this material. So we'll review on Monday for the exam on Wednesday. I'll post on the website under today's lecture a practice exam that we can go over on Monday. Again, try to work through that before Monday. The exam will be open text. I will try to put together a summary sheet of the formulas we've covered since the last exam with regard to electromagnetics. Actually, it was on that handout, the previous one for electrostatics, but I didn't actually update that site to use the same notation as our textbook is using. So I'll try to get that done for you by Monday as well. So the textbook actually concludes with a discussion of polarization and power flow. But I didn't quite cover everything I wanted to about plane waves. In particular, one of the homework problems used a general expression for a plane wave, and I wanted to make sure we covered that so that you could do that problem. So in the previous lecture, what we assumed is, again, we're jumping back and forth between this phasor representation for an electric field, which doesn't have any time variation, and expression for the field itself, or again, E0 here in the phasor representation might be complex. Cosine omega t minus beta z plus psi, which would be then the angle of this E0 constant. It seems like a fairly particular case. The E field is x directed with propagation in the z direction, and we found but we can generalize it. But we found for this case, the magnetic field intensity is given by this expression. Okay. So it's very similar to Ohm's law, except we're working with electric field and magnetic field here. The units, even electric field is volts per meter. This magnetic field intensity is amperes per meter. So, they only differ by this eta value, the intrinsic impedance of the material, which means that if we have one, we can calculate the other. Given E, we can easily find H. Given H, we can easily find E. It's a little more complicated than just dividing by eta, because they are in different directions. They're 90 degrees, right? They're perpendicular to each other. So the other part is finding out the field direction. But just remember that H is always a plus 90 degree rotation from E. And I'll give you formulas for actually finding that if you don't want to use that trick. Well, when the propagation is in the plus C direction, that is, so. And these formulas, plus C direction. For propagation in the minus C direction, the minus signs here in front of the beta Z actually become plus signs. Now, more generally, for E in an arbitrary direction, and I just got a unit vector E here, and then everything else will be relative to this E unit vector. And then K dot R dot, where K is a wave vector and R is our position vector. And then in the time domain, cosine omega t minus K dot R dot plus psi again. So it's really just a generalization of these results that we have for the specific case where E was X directed, H was Y directed, and direction of propagation is z. Now E is in this E direction. The direction of propagation is in the K direction. So if we divide K by its magnitude, we get a unit vector in the direction of propagation that we're calling K hat. We also have, it's for plane waves, we also have this condition that E dot K is equal to 0. The direction of the field, of both fields, is actually perpendicular to the direction of propagation. And then another figure that it's not an easy thing to visualize. So this is, you have to remember, this is a snapshot in time. And so it's showing in the Z direction how the intensity of our E field varies with space, but it's always in the X direction. Now, just an instant later, this peak would move to the right, okay, an instant in time later. And that's what the wave propagation means, that the crests are moving to the right, just like ripples in a pond. At any instant, this right now at this instant it's peak, but it's time varying because of the cosine, the sinusoidal variation. So, sometime later, this is actually going to be 0 at this point. Okay? And then the electric field would actually cross 0, would peak here where it's 0. But it would still be in the same direction, still in that same E direction. The other thing that we notice from this is that, again, the H field is perpendicular to the E field, and both are perpendicular to the direction of propagation. So we've been working with this simple case where E is an X-directed, H is Y-directed, and the direction of propagation is in Z. So generalizing that, gives us these formulas. Propagation. And we can write the corresponding vector formulas for calculating H from E in either the phasor form or in the time varying form. So these would be true in general. They are true for even our specific case where our direction of propagation is in the Z direction, and Z cross X would give us Y. Okay. That's this first formula. So we could get H from E by Z, which is our direction of propagation, cross X. Yeah, would give us Y, and then we're dividing by 1 over eta. Okay. Oh, or we could go the other way and find E from H by, in this case, it's in the phasor form, it's minus eta K cross H. The cross product here is just to get the 90-degree rotation. Or in the time domain, it's minus eta K cross H. where in all these cases, the direction of propagation of our E field is perpendicular to the direction of our E field is perpendicular to the direction of propagation. So we write that using vector notation by saying that the dot product of the two vectors, or the dot product of unit vectors in those directions, is equal to 0. So that implies perpendicular, that they're perpendicular. So E and K have to be perpendicular. So let's look at an example. And I think one of the homework problems I gave last time is similar to this. Actually, I think it's a little simpler than this problem. So this would be an expression for an E field that's in an E direction, some arbitrary, pick a direction, and we're going to find H from that. Now, bound up in this term that's K dot R, that 2x minus y. So by comparing to this form, we see that 2x minus y has to be equal to K dot R. So it's that term that will allow us to actually find the wave vector K. The other requirement is that E has to be perpendicular to that wave vector K. Here, we're also given that E is x hat times 1 over square root of 5 plus y hat 2 over square root of 5. It's a unit vector, so the square root of the sum of the squares of the components has to be equal to 1, which is the case there. And the vector perpendicular to the direction of propagation, that defines a plane, right? We've got a vector. There's a whole plane of vectors that are perpendicular to any particular vector. So this is one vector that lies in a plane perpendicular to the direction of propagation. Perpendicular to both of them will be our H field, will be the direction of our H field. So that's the problem here. Find H. We'll do a little more than that. But from our notation, from what we're given, so generally, K is my unknown vector. So I'm just going to write it down in component form with 3 variables. I don't know the x, y, and z components of K. Okay. My position vector, though, in Cartesian coordinates is x hat x plus y hat y plus z hat z. That's always the form for the position vector to any point in Cartesian coordinates. So carrying out that dot product, you get kxx plus kyy plus kzz. Now by comparison, and this term in parenthesis is equal to k dot r. So by comparison, this expression has to be 2x minus y. So that implies kx is equal to 2, ky is equal to minus 1, and kz is equal to 0. So my k vector is x hat 2 minus y hat. So in this particular case, this is in This is in the XY plane. Our direction of propagation is in the XY plane. And E is also in the XY plane. Okay, since both these vectors are in the XY plane, we know that H has to be perpendicular to them. H has to be Y directed, and that'll fall out of the math in just a second. So this is the vector K, the unit vector in that same direction. We just divide by the magnitude of K is 5, or square root of 5. So this would be 2 over square root of 5 minus y hat 1 over square root of 5. It is also true that beta, our wave number or phase propagation constant, is equal to the magnitude of our wave vector. So beta here is square root of 5. I know there's a lot of equations, but beta is also directly related to our wavelength. That's 2 pi divided by the wavelength. And you can verify that E dot K is equal to 0 as required. So I can't arbitrarily pick E and K vectors. I have to make sure that they're perpendicular, actually. So for plane wave propagation. In phasor form, we have E10, e to the j, 45 degrees, e to the minus j, k dot r. And you just get rid of the omega t dependence. So just like working with phasors back in circuits too. So I had to do a little work actually before I could solve the problem for H to find K. In particular, I needed to find this K unit vector. So now I can use this expression to find my phasor form for H. So H is 1 over eta K hat cross E hat, or K hat cross, sorry, not E, but E tilde, it's a phasor. That's K hat cross E hat, 10 over eta e to the j, 45 degrees, e to the minus j, k dot r. Then will be our expression for H. We've got K and E, so we can do this cross product. K is 2 over square root of 5 minus y hat 1 over square root of 5. And E was given. It's x hat 1 over square root of 5 plus y hat 2 over square root of 5. Again, since both of these vectors are in the xy plane, the cross product has to be equal to y. Okay. Could be plus or minus y, though. That's the only thing that's unknown is the sign. So we can, carrying out the cross product here, I'll write the full form. But for the x component, it would be the y component of this times the z component of this. Well, that's 0. And then it would be the y component of this times the z component of this first vector. But there are no z components. So again, And that's what we should get. Right? And similarly for y, it would be the z component of this vector, but there is no z component, times the x component, and then the z component minus the z component of this times the x component of the first vector. Again, that is 0. And finally, the z component would be the x component of our first vector. And that is not 0, times the y component of my second vector, minus the y component of my first vector, which is minus 1 over square root of 5, times the x component of my second vector. So I'm going to get 4/5 plus 1/5 or 5/5 or z. I knew it had to come out to be unit magnitude, but because it's a cross product of two unit vectors. Again, I knew it had to be either, because both vectors were in the xy plane, I knew the direction that h had to be z directed. So let's see. And then 10 over eta is 10 over 377. I don't think I put that down over here, but in the problem statement, I should have indicated this is free space. So the intrinsic impedance is the intrinsic impedance of free space, which is 377 ohms. It's the square root of the product of U0 and epsilon 0. And that turns out to be 26.53 milliamps per meter. So that finally gives me, I can put all the pieces together to get H. It's Z directed, 26.53 milliamps per meter. Same phase angle as e to the minus jk dot r. Have the same direction of propagation. So, or going from the phasor form to the time domain expression, I would have 26.53 cosine omega t minus 2x minus y, which is k dot r, and that's the same term as from E milliamps per meter. There's some additional information that's embedded in here. Beta is actually equal to the magnitude of k, which I said was square root of 5. We also know that lambda is 2 pi over beta. So that turns out to be actually 2.890 meters, 2 pi divided by square root of 5. And since we're in free space, that also determines the frequency. So even though I didn't give you omega, we can actually find out what it has to be. The frequency is the phase velocity divided by lambda, but since we're in free space, the phase velocity is the speed of light. And that turns out to be 106.8 megahertz. So one of the homework problems that I gave actually is similar to this. I want to briefly mention wave polarization. Actually, I'm not going to go into any detail on this. It doesn't go into any detail in the book, but I'm sure you've heard of the term polarized light or polarized glass. And what we've been looking at is in the Phasor form, e to the minus j beta z. The electric field here is always in the x direction and is said to be linearly polarized. Okay, that's still this picture. Our H field is also linearly polarized. It never changes direction. The E field is always x directed, the H field is always y directed, and the direction of propagation is z. So this is linear polarization. If E is actually changing directions, and we'll see that that's possible. You know, it may actually change direction with time in the xy plane. H would also change direction, and they would always be normal to the direction of propagation. But it is possible for x and y to actually be rotating in the xy plane, not be in fixed position. And then that leads to other types of polarization. The most commonly encountered is what's called circular polarization. So more generally, our E field could consist of both an x and y component, or E is equal to x hat EX plus y hat EY e to the minus j beta z. Now, to get the different forms of polarization, you have to remember that EX and EY in general can be complex. If they're both real, are both real, or they could actually be complex with the same phase angle. But if they have the same phase angle, then we can write E is actually x hat cosine of some angle plus y hat sine of some angle, and I can pull out a magnitude minus j beta z. This is still linear polarization. It's just polarization at an angle relative to the xy axis. Okay, and that's what this figure is actually supposed to be showing here. E is still the direction of E is still in the xy plane here. The direction of propagation would be, as would H, but the direction of propagation would actually be out of the board. And that's what the dot is showing there. Where here, E rho is actually square root of the sum of the squares of the EX and EY components. And cosine of the angle is EX over E rho. And sine of phi is Ey over E rho. Okay. This is still linear polarization. Okay. The E field is not changing direction. If Ex and Ey differ in phase, the field will rotate in the XY plane. And what that really means is it appears to rotate, and it still has the same X and Y components, but at one point the peak will be in one direction, and if we look at the peak intensity, it appears to rotate in the XY plane. So the most common case, or I guess a classic example rather, if Ex is equal to E0 and Ey is equal to E0 times e to the j pi over 2, which is j. So these two complex numbers have the same magnitude, but they're 90 degrees out of phase. The field will rotate circularly. So if they're 90 degrees out of phase, and again, this is just the E field that we're talking about. You know, one instant in time, we're going to have a maximum in the X direction. A quarter cycle later, the E will be entirely in the Y direction. So it appears to be rotating in the XY plane. H will also be rotating in the XY plane, perpendicular to the E field. So I'm not even going to attempt to draw some of these pictures. So this is, if you can decode this, and you have to look at the colors, Ex is shown in blue. Okay. Ey is shown in red. No, I'm sorry, Ey is shown in green. X-axis is perpendicular. Y-axis here is horizontal. And then the vector sum of the two is red with the black arrows. And it's showing here at this particular snapshot in time, both are kind of peaked here along the X and Y axis. So the E field would be directed at 45 degrees relative to the negative Y axis. And then at this instant, they're both 0, and at this instant, so they'll both be 0. So those components are changing up and down, so that the direction of our E field will appear to actually rotate in the XY plane. Okay. And that's called circular polarization. Circular polarization. And you can generate these different types of polarization depending on your antenna structure. Now, unfortunately, we're not getting into a discussion of antennas. That would be in the second semester, where he covers antennas and how to actually generate these from antenna sources, how to generate the fields from antenna sources. But depending on the direction and orientation of the antenna, you can get linear polarization, vertical polarization, for example, or horizontal polarization, or with an antenna that's in the shape of the cross and you're exciting both components simultaneously, you can get circular polarization. Now, typically, you'd want your receive antenna to be in the same orientation as your transmit antenna. So typically, you would use horizontal polarization for both, perhaps, or vertical polarization for both. There are times when you may not know the orientation of one antenna or the other. Then it's advantageous to actually use circular polarization. An example of that is in some satellites, they actually transmit using circular polarization because the orientation of the transmit antenna isn't known. But with circular polarization, we can still pick up some component of the transmitted electric field. So he has, this is actually showing a picture of a circular polarized wave in red, resulting from the addition of two linear polarized waves, EX and EY. Notice that they're 90 degrees out of phase here, and how the field will appear to rotate. And this is a little better picture of that, showing circular polarization. And depending on whether the angle is plus 90 degrees or minus 90 degrees, you can get what's known as left circular polarization or right circular polarization, based on, unless my depth perception is wrong, it's supposed to be in one, you put your thumb, right hand thumb in the direction of propagation, and your fingers curl in. That appears to be this one though. So I may have got these figures reversed from the textbook, and then, or I'm just not seeing the figure properly. And this is left hand polarization, depending on the direction of rotation compared to the direction of propagation. Okay, the last thing I want to mention, the last topic is power propagation or power flow. So we've been considering this case, so let's go back to it. E to the minus j beta z, or equivalently, in the time domain, beta z plus psi. And E0 over eta, e to the minus j beta z. And in the time domain, 0 over eta, cosine omega t minus beta z plus psi. So just like with circuits and dealing with sinusoids, you know, we have the concept of instantaneous power, but we're typically more interested in average power. But here, since the E and H fields are propagating, we have power actually propagating in a particular direction as well. Power propagates in the direction of propagation of the E and H field. So really, when we've been talking about the direction of propagation, that's the direction of power flow from these fields. The instantaneous power density is E cross H. Again, these are time domain expressions. This would have units of watts per meter squared, and it's called the pointing vector. And it's not because, although power flow is pointing in that direction, this is a guy's name who first came up with these expressions. So this is called the pointing vector, and it's E cross H. Now for our particular uniform plane waves, we could carry this out, and it would be then cosine squared omega t minus beta z plus psi, using those two expressions for our E and H field in the time domain. Okay? And this would be watts per meter squared. So we actually have to integrate this over an area to get the power through that area. Now, typically not interested in the instantaneous power, but rather the time average power. And it's more simply expressed from the phasor form, from the phasor field vectors. And it's 1/2 real part of E cross H conjugate. Now these expressions may remind you of some of the complex power expressions that you encountered actually in circuits 2. And they are directly related. You know, there we talk about complex power as being V times I, and then the real power is the real part of complex power. So the same definitions here. You know, you'll have the factor of 1/2 or not, depending on whether the phasors are expressed in RMS form or peak form. Here we've been using peak form, the amplitudes throughout, the peak amplitudes. So we have a factor of 1/2. But if you express the phasors using RMS amplitudes, you actually get rid of the factor of 1/2. Unfortunately, that's always annoying, but always present. So for planar waves, and we can carry this out, and the average power is it has a direction. That's what makes it different than power that they work with in circuits, where the power is always directed along the wire. But here it's in free space. And this may remind you of V squared over R, or, you know, that would be the RMS expression. In terms of peak, it's the peak voltage squared divided by 2R. So similar expression here in terms of, and you could also write it in terms of the magnitude of the H field. The average power through an open surface would be given by integrating our power density over that surface area. Unfortunately, you know, I've really just run out of variables at this point. You know, I've had trouble already trying to express differences between phasor notation and vectors. Same thing here, I mean, overusing S. This S average is a power. This S is a surface, but we've been using this notation for a surface throughout the semester. So we would actually integrate that average power density over like the area of our receive antenna, if it's a dish antenna, for example, to get the amount of power that's intercepted by that particular antenna. All right, I think that's it. That's everything the book has to tell us anyway. So I'll post a practice exam on the lecture site for today's lecture. So we'll go through that on Monday, as well as look at any homework problems they might have questions about. I will see you later. So I'm pretty sure everyone will be bringing the book to the exam on Wednesday because it is open text, but I do need to collect the textbooks at that point.